Thank you very much. It's a pleasure for me to be here at this conference. Let me give you just an overview of where I'm trying to head in this talk. Is our climate changing? I think that's already been covered by many of the speakers yesterday. I'm going to say something about what's in climate models, the verification of climate models, model projections of past and future climates, mitigation versus adaptation. Now, I'll give you some sort of new information about what's happening in Washington, D.C. I have a second job, and that is I'm chairman of the National Science Board, which oversees the National Science Foundation, but also advisors on Congress and the President. And then finally, I'll say something about scientific freedom for government scientists. I think you've seen on this figure in various ways, but 2005 is either on the warmest or is tied for the record year, essentially showing the same sort of trend over the last 20 or 30 years of a very the rapidly warming planet. Here I've taken from a NASA satellite the changes of sea ice up until on the present, and then if you extrapolate that in a very linear fashion, you can see that the sea ice shrinks to a very small amount in the summertime by the end of this century. Obviously, we can actually model this in our climate models. Here, I just want to give a status of the state-of-the-art climate models and their transition to Earth system models. The time that I started on this at NCAR was about 1964. So I've been engaged in climate models right from the start. At that time, climate models were either atmospheric models or ocean models. And then as we went into the 1970s, we added things like sea ice, and we actually tried to couple on these models to get early forms of a climate model. As we entered into the 1990s, we've added such things like sulfate aerosols, the carbon cycle, dust and sea spray, and interacting with the vegetation, and some aspects of the biogeochemical cycles. Now, when you add all of this complexity into climate models, obviously things get worse because you don't always know the interactions, and so on the modeling actually steps back a little bit as there's an intense effort to try to get the models to essentially do on the correct things, and it's all and many of the very difficult areas have to do with how much, for example, carbon goes into the soil and how much goes into the ocean, and those are still unknown aspects, and so you have to try to understand those fairly well before you put them into a computer model. So there's always a limitation as we try to advance on the capability of these models that there's uncertain knowledge. Just to give you a very quick schematic of what's in a model, we essentially take into account the solar radiation coming into the system. We have several different kinds of clouds: stratus clouds, cumulus clouds, cirrus-type clouds. We obviously taking into account the complex sort of radiation, both the solar and infrared radiation interactions in the atmosphere with clouds and a water vapor and other greenhouse gases. We have snow, soil moisture. We have river flow into the oceans. We have the oceans with all of their complexity and the dynamics. And all of these things are things that we've improved upon very significantly over the last 30 or 40 years. There's still some problems, but the models are looking more and more realistic. And I'll give you a few examples of that. Now, we're always limited by the speed of supercomputers. In the sort of the 1960s and early 1970s phrase, we had models with this kind of sort of resolution. You can see it in terms of the blocky kind of continents. Now, as we sort of move into the present era, we can have models that have this, have a very high sort of resolution, both in the ocean as well as over land. For example, in the early days, we had maybe only one grid point for the state of Utah, so you really couldn't put in accurate sort of representation of the mountains. Now we have maybe 10 or 15 sort of grid points for a state like Utah in our models, and that means that we can improve it. So we're always trying to keep pace with what we can do with the computing capabilities. Here I just want to give you an example of that same grid for a model in the 1960s versus the present scale models that we're either using. Here I want to show on the water vapor content. This is for the water vapor from the bottom of the atmosphere up to the top. And here we can get a very sort of realistic sort of view of the circulation systems. You can see that sort of trade wind areas that the flow is essentially going from east to west, and then the moisture is being picked up in essentially warm front areas and taken up into higher latitudes. On the orange areas are places where on the precipitation is actually occurring. So you can see storm systems, sort of cold air coming down from the higher latitudes, and it doesn't have much moisture, and the tropical air going up to higher latitudes. So when we look at these figures, we can compare them with observations, especially satellite and so forth, and they are getting very sort of actually looking at in a very circulation features that look quite real. If we can also do the same thing with ocean circulations. Here I just want to show ocean eddies. This is a very high resolution model, fairly high sort of resolution model. You see eddies right along the equator here. Travel around, you see in the Gulf Stream going up. If you go high enough resolution, you can actually take into account on the flow through the Indonesian Straits into the Indian Ocean. In order to sort of do this, you have to have very high resolution models that you can run on supercomputer systems. So when you look at this, we can virtually capture every ocean basin. And I want to give another example of this when you go to even super high resolution. This is of the order of 10 kilometers globe. And you'll see in a minute that there are eddies in the ocean, and they're ubiquitous. They're virtually everywhere. And you can get these very realistic sort of simulations. And in fact, you can capture on the Gulf Stream here, showing on the meanders in the Gulf Stream, so that we've come a long ways in being able to sort of reproduce the eddy structures in the world's oceans. Now, there are other aspects in the climate models that are very important to make them believable. In other words, are we generating El Niños and La Niñas in the correct places? Are the storm systems working in the right way? And I think that with El Niños and La Niñas, which happen in the Pacific along the equator, on the models still have a ways to go. We generate them with a frequency of roughly 2 to 4 or 5 years, but they don't quite have all of the realistic features, and so we have to make some improvements in our models there. Monsoons, and we do a good job with. We can capture the Indian, Asian monsoons and the other monsoons around the world in a very sort of a you can almost count on the time that they are on set. Say, for example, in India, and our models are very close to capturing on the features in a realistic way. There's something called the North Atlantic Oscillation and the Arctic Oscillations. These are kind of oscillations which are a very important component of the climate system, and they're essentially natural oscillations in the system, so that they actually give a part of the natural variability of the climate system, and our models do capture those at roughly the right frequency and amplitude. One of the very critical things is sea ice, and you've heard some presentations on sea ice. And I wanted to just point out that if you look at the climatology from 1979 until 1999, on the right-hand side, and we have the observed climatology. Here's on the wintertime sea ice. You can see on the extent in the red. And over here is the summertime sea ice distribution in terms of concentration. And on the left over here is the winter, so it's pretty close that we're able to capture much of the sea ice concentration. Although there seems to be a bias towards, in our model calculations, having too much sea ice. In the summertime, there's obviously less, but we're fairly close. Now, this is a real improvement for our previous climate models, because sea ice tended to be a hard thing for us to get right, because it's a very sensitive parameter in our models. Now, we actually use on the distribution of the volcanic eruptions to include in our models as we try to reproduce the historical climate going from 1870 up until in the present. And the reason I include this figure is that the volcanic events are very important for including our models, because what happens when a volcanic event like this Mount Pinatubo erupts, it actually cools off on the climate for a few, maybe 18 months, maybe 2 years. And so that our climate system kind of bounces back after the aerosols leave on the stratosphere. But they also give us a calibration on the forcing caused by aerosols. And so that gives us a way to sort of verify, are we including on the right physics in our models as we try to include the volcanic eruptions. Here's a figure that I took out of Time magazine, 2001, essentially showing the sources of carbon dioxide in the atmosphere. I think these numbers probably need to be somewhat revised, since China and India probably have increased their putting of carbon dioxide into the atmosphere. But anyway, I think it gives you a rough idea that the U.S. and Europe are certainly on the two largest sources. And of course, in the future, it's going to, on that distribution, is going to change somewhat. But clearly, on the United States, is going to still be a very large source of carbon dioxide. Now, when we actually carry out these experiments using climate model to look at future climate change, we first actually do a historical simulation. And I just only specify the carbon dioxide. Just imagine that we have methane, nitrous oxide, other greenhouse, and CFCs that we specify, going essentially from 1870 up until in the present, so that we have that record of concentrations that we can include in our models, so that you really know that you're forcing it properly. Now, when we sort of go past the year 2000, we actually do a group of scenarios. One, of course, is this thing called A2. A2 is like a business as usual. In other words, don't do any curbing of greenhouse gases and just keep using sort of on the past practices. I think most people feel that A2 is probably not realistic. It's as if we sort of ignored all of the warnings. The other extreme is the commitment. In other words, if we could magically stop the concentrations at the year 2000, how long would it take for the climate system to settle down to a new climate? And so that's what we call commitment. In other words, on the climate's going to change even if we took the most drastic actions in terms of greenhouse gases. And then the other two are sort of in between. A1B is one that's often used where greenhouse gases go up to the year 2100, then they flat. Or if are on sort of this B1 actually has it level off at a lower concentration of just a little bit over 500 parts per million. So we typically run ensembles of these experiments, like 5 runs, and we generate huge archives of experiments that scientists plow through. Our archives are roughly 150 terabytes of data, and we make that available to anybody in the world to examine. Now, I'll just sort of repeat a little bit here. This is the same figure I showed in the previous one. Here I show the change of surface temperature, and here I show the change of sea level. So even if you freeze on the greenhouse gases at the year 2000, you'll see that the warming of the planet still goes up just because there's an imbalance at the top of the atmosphere. And so in spite of whatever you want to do, the planet's going to keep on warming even if you freeze on the greenhouse gases. So you can see an enormous range going all the way up to maybe 4 degrees warming by the end of the 21st century, and even more if you go out to the end of the 22nd century. Now the interesting thing is the sea level rise keeps on going. It doesn't level off after a few decades. It actually keeps going up, so that we're committed to substantial raising of the sea level from just on the fact of the warming of the ocean. Okay, now as you heard yesterday in many of the talks, that the glaciers are melting at a very rapid rate, so that's going to be an additional factor on the raising of sea level. And if you look at the geographical pattern for each one of these scenarios, this is business as usual. You can see that there's very substantial geographical warming in the high latitudes and overland areas. And there's less with the other scenarios. Here I just made a little animation of the climate warming, which is available. You can download high-resolution versions of this animation. Basically, what we did was we assumed that the climate at 1870 is a baseline, and so that there wasn't a great deal of change. So what I'm showing is the anomaly from that 1870 period. And as this animation goes forward in time, you'll see that the globe actually turns redder and redder. And you even see some events. For example, you'll see El Nino events and La Nina events showing up. There's a couple right there. Now, several things happen when you sort of warm up on this planet. The Gulf Stream actually shifts to a more southerly route, And you get actually a little bit of cooling north of the Gulf Stream because it's not taking as much heat up to the higher latitudes. You can see that most of the warming is taking place over the higher latitudes. You're starting to see a little bit of red by this time here. You're actually getting a cooling right along off the coast of Antarctica, and I can explain that. Now here's that cooling from the change of the Gulf Stream in the North Atlantic. So by the end of this century, there's a great deal of warming, and most of this is probably caused by the changes of the sea ice and the snow cover in the high latitudes. So this gives you some sense of what a climate model sort of gives you. Let me skip that one. Now, climate models can help unravel what forcing is causing what. Obviously, our real climate system is very complicated with lots of factors going on. So what we're able to sort of do in our climate model is to sort of run it over and over again with the various factors turned off or turned on. Here I want to show the globally average temperature going from 1870 to the year 2000. And here I want to show, if you just put in natural forcings are the volcanic forcings and the solar forcings. And you can see that just having, it's here in blue, if you go out to the year sort of 1960 or so, natural forcings explain a lot of this early warming of the planet. However, if you go from 1960 to the year 2000, natural forcings actually would cause a cooling of the planet, and some of this is caused by the volcanic eruptions on some of these sharp, colder spikes right here are actually Mount Pinatubo and other major eruption events. However, if you add in the anthropogenic, which is essentially all the greenhouse gases and the sulfur aerosols, you can see that you can reproduce the observed climate sort of warming in the last part of the 20th century. So that, in a sense, you can sort of unravel which of the forcings, or the natural or the anthropogenic, are causing on this rapid rise in the temperature in the last part of the 20th century. So climate models allow you to dissect it and look for that smoking gun. Now, obviously, a lot of the things that we look at are time mean variables. But what really impacts humans in terms of their health and other aspects are looking at how the interesting aspects of climate change affect things like heat waves. And here I just want to point out that heat waves are very important for the mortality because they have a big effect sort of at the times that they occur. And just to show that we're not completely wrong in how we deal with this, I want to show over here on the right-hand side the 3-day minimum temperature for the observed. Here's the U.S. and this is Europe. And here you can see on the pattern of heat waves in both places. And here's if we just do our model calculation, and we get generally the same pattern, so that the model is able to capture the same sort of statistics that you find in heat waves. Now, if you look for the end of this century on the future, well, you can see that we can expect a lot more heat waves on the west coast and also in the southeast part of the U.S. Also, in the pattern for heat waves is going to be moving north in Europe. So we can give some information about this, and this could have some influence on a whole range of our activities in terms of the infrastructure of the climate, of how people adapt to future climate change. Now here I want to show a controversy which is still not fully resolved, and that is even though on the greenhouse gases are essentially going to increase, on the lower part of the atmosphere from our model calculations should actually warm up substantially. Now, kind of one of the later speakers is going to be speaking about this in probably in some more detail, but on the way it should work is the lower part of the atmosphere should warm up, and the stratosphere, which is right up in here, should cool off as you increase on the amount of greenhouse gases. It's complicated by the fact that you also have ozone to sort of take into account. On surface temperature ought to increase. Now, on the controversial part is what do the observations show? And here the observations have a varied history because of the difficulty of actually measuring small changes. But anyway, I don't think, at least I don't think there's a great deal of inconsistency in between what the models are showing and what the observations are showing. Oh, back up here. Now, there's another way to also look at climate change. We've been mostly concentrating on surface temperature, atmospheric temperatures. But we can actually look at the ocean temperatures. The oceans have also been responding to climate change. And here, if you look at the blue area, and the reason there's a spread is we have an ensemble of experiments. If you look at the temperature change, say at the start in the controlled experiment, where you don't have any increase of greenhouse gases, it's the blue area. So you can see that there's a blue area for each of these ocean basins. This is North Indian, Pacific, North Atlantic, South Pacific, South Pacific, and South Atlantic, and South Indian. Now, if you look at the trends from 1955 until 1999, you can see that the oceans have warmed up, and the observations are in the red, and our model calculations are in the green. So you can see that our models is able to capture the observed warming in each one of these ocean basins. And so this is another verification of not only warming of the climate in the oceans, but that we're able to capture it in our ocean calculations as part of our climate models. Here's another one showing the sea ice change. Here we're actually showing the observed is in this little blue thing right here. I mean, little sort of yellow thing going from 1880 to the year 2000. And I want to draw your attention to the summer one, where we're fairly close to the observed. But as you run this out to the end of the 21st century, that the sea ice in the northern hemisphere summer almost disappears. Okay? So that this is very alarming, and I think that the earlier speaker yesterday spoke about the changing of the sea ice. So I don't think this is a small perturbation. This is likely to take place if we don't do something. Now here now that this happens for the A2 scenario on the business as usual. If we're able to somehow mitigate or sort of account for the greenhouse gases and curb them in some sort of way, you can see that we can actually preserve on the sea ice. It's going to still go down in the B1 scenario, but it won't be going down as much. Another thing to show is the precipitation intensity. We find in our model calculations that the rainfall rate or the snowfall rate actually increases. That's essentially shown over the large parts of the globe. And it's easy to understand. You warm up the planet, and you actually cause on the rainfall and snow rates to increase because there's actually more moisture in the atmosphere. Let me skip over this, because I think on the sea ice, or the sea level actually changes, and I think that it was covered, I think, in some of the other ones. Here I want to show changes in hurricanes and tropical storms. We're able to run, on the Japanese have done this, we haven't quite done it at our place yet, but we're doing it, sort of run very high resolution models that capture the hurricanes and fairly well with sort of realistic eye walls and eyes and so forth. And what you find here is the observations in the top, the present day and the future. And what you get in these model calculations, several groups have done this, is that you get fewer hurricanes, but they're more intense. Okay, and so that I would say this is early research, and it's going to be verified probably by several groups around the world. And if that is true, then I think we have some major problems that the world will have to face, especially in coastal areas. Ongoing activities, high resolution, as I pointed out, full hydrological cycle, including ice sheets. We're adding ice sheets into our model so that we'll be able to take into account some of the dynamics of large-scale glaciers, such as Greenland and Antarctica. Improvements in clouds and aerosols and so forth. I'll skip through this real quickly here. I want to get down to the point. One of the questions that hasn't seemed to be brought up very much in this symposium is, should we geoengineer the planet? To an environmentalist, that's a scary thing to think about. But what happens if we find ourselves in a situation where the global temperature increase is increasing of the order of 0.6 degrees per decade? I would imagine at that point people would be willing to consider, can we mitigate? And if there's time for those questions, I'll be able to try to give some insight on that. Let me skip to, 'cause I'm almost here. I want to end up on the perceptions of news coverage. This came out last a week and a half ago as part of the National Science Board's Science and Engineering Indicators. You can Google that and find out. It's a huge document, 1,000-page document that shows all kinds of trends and statistics. But it's interesting to sort of see that the public's perception of the news coverage on global warming going from 1997 to the year 2005 is actually increasing. That's encouraging. It's not going as fast as I'd like, but it's increasing. So that on the perception that on news coverage is generally correct is actually increasing. Now, the new concerns in Congress on the scientific freedom for government scientists. I received a request as chairman of the National Science Board a week and a half ago from Senator McCain, a request to carry out a study to look at the policies with respect to the suppression of scientists who are governments supported. So we'll be looking at the policies of each of the science agencies. And it doesn't only refer to climate change, but all of the other societally sensitive areas. And then on Thursday, I had the privilege of representing the National Science Foundation along with the director at a hearing on the budget for NSF. And the bottom line is a very strong support for science in a very nonpartisan way. So I'm hoping that the increases that are being outlined, at least for NSF, are going to actually be carried through. So that there was also a lot of statements by the Congress people who actually came to the hearing and queried us that they are in strong support of evidence-based science, and that will be something that is nonpartisan. And I'll just end with this here, and in terms of where the action is going to be taking place over the next few years. Thank you very much.
Does your model deal with water availability such as groundwater levels and those parameters?
Yes. What we have in our model is a very complicated land cover scheme where we take into account even subgrid scale features like different vegetation types, several layers in the soil. I forgot, maybe it's like 10 soil layers. We keep into account the water vapor, and we actually keep track of the permafrost. In fact, one of my scientists who's in my group, he's recently published an article in the GRL showing that by the end of this century, permafrost will be essentially all melted at the top. So, yes.
As we all know, the temperatures have risen globally and in the northern hemisphere in recent decades. But I believe it's true that temperatures have either declined or at least not risen in the southeast quarter of the U.S. And what's the reason for that?
Southeast quarter.
Roughly. Southeastern part of the country.
Okay. Yeah, I think there's probably people here in the audience that can answer that question better than I can. But what we typically look at are the global aspects, on the large regional aspects. But there are going to be some places where just from the normal variation of regional climates, I think things change. Now, one of the factors that could be an aspect of that we try to take that into account, is changes in land cover. You know, humans have been changing land cover in a very significant way, and that could also be a big determinant in how the climate responds in some of these smaller sort of regions.
Land cover has changed over the U.S. as a whole, certainly in the Midwest,
Yeah.
for example.
Yeah, I don't think
consistent through recent decades.
Yeah, I don't think I have a good answer. I think there's on the people that really look at regional climate change. Oh, okay. I think John Christie is going to cover that question.
What do you mean by geoengineering?
Well, I don't.
You mean dumping stuff in the ocean to make it salty or basic?
Well, I can tell you some real drastic things. You know, there's a whole litany. There's a guy by the name of David Keith who's actually written an article on this, and also in the back of the book that I wrote on climate modeling, I have a little chapter on various schemes. For example, just give you, if you want to think about sort of wild schemes, Edward Teller had this scheme of you would take up a 747 and fly it up every day and dump a lot of aerosol into the stratosphere, and that would act like a volcanic eruption, and that it would essentially sort of decrease on the solar input into the climate system. There's also another scheme to put up huge shields at something called is it the G1 point? It's the point in between the Earth and the Sun, where if you put up some kind of shield that you can cut back on the solar flux. So there's all kinds of schemes that people have come up with. In fact, I got a cartoon from some guy that actually wanted to build a big kind of tunnel that would take the cold air and take it all the way down to the tropics and cool off the tropics. Now, some of these are hairspring harebrained ideas, and other ones I think have some feasibility. For example, even dumping the iron into the ocean has been looked at, although it's not as simple as some of the early ideas about that were essentially taking some of the carbon dioxide out of the system. So there's a lot of things out there that might be considered if we got into a period of very rapid warming of the climate system. And there's probably no simple sort of solution. Yes.
Question I'd like to ask you. It seems to me scientific community is clearly documenting the problem. Is there a forum now to really conduct this assessment of mitigation of what we should do? It's the same rational scientific strategy. You know, putting all these issues on the table, what are the options? Plus and minus nuclear power versus geoengineering, and really say, okay, accepting where we are and where we might be, is there any thought of the scientific movement supported by international bodies?
I don't see a single body. I see a lot of people kind of nipping at the edges of this problem. And, for example, the National Academy of Sciences, on the various foundations, international bodies such as the World Meteorological Organization, all of them are facing up to this is a big problem and how to deal with it. But I don't see a unified way to deal with it unless the leaders of the world decide that this is a serious issue. And, yeah. Yeah.
We don't need to be political leadership. We're just saying the problem's real. Now we're moving forward.
Yeah.
Consider.
Well, I would like to see that. I don't quite see it happening yet. Yeah, right. Let's see, right back there. Oh, is that wrong? Oh, go on.
From a statistical perspective, what's been the most surprising variable and popped up in your model? And I mean, looking both backward and forward, and what have you come up with mathematically that drives its impact in your model?
Oh, gosh. I don't know if I have a simple sort of answer. I think that the real challenge for us now in the future are two areas. One is on the role of the aerosols and their interaction with clouds. And the other is taking that step from going from a climate model to an Earth system model where you include on the biological and the biochemical interactions. I think those have been more challenging than we would have thought when we first started. But we're making progress, and obviously the models aren't perfect, but they do reproduce a great deal of what we understand is happening in the climate system. Thank you very much.